Hello lovelies, in this video we're going to be going through your Cambridge International A-Level Paper 2 that we've written for 2024, so you need this for the AS and for the full A-Level. Now, this is a very content heavy, there are lots and lots of questions in here, so I want you to focus on the exam skills, how we can go through this quickly and how you can show up to the examiner so you know what you're talking about.
A student wants to determine the empirical formula of an unknown compound X, which contains 0.24 grams of carbon, 0.38 grams of fluorine, and 1.42 grams of chlorine. Find the empirical formula of the compound X. So the way that I like to do this is I like to write down the elements I'm talking about along the top. So here, C, F, and Cl. And then I do 3 rows, M, Mr, and N, the number of moles. So I'll fill in the masses in the mass row, and I'll fill in the MRs of the carbon, the fluorine, and the chlorine in the MR row. Then to work out the moles, all I need to do is do the mass over the MR. So for carbon, that's 0.24 over 12, which gives me 0.02. For fluorine, that's 0.38 over 19, which again is 0.02. And for chlorine here, I've got 1.42 over 35.5, which gives me 0.04. So we've got the number of moles, but we want the simplest whole number ratio of moles. So to do that, we just divide by the smallest number of moles here. So I'm dividing each of these through now by 0.02. That then gives me 1 for the carbon, 1 for the fluorine, and 2 for the chlorine. And so therefore the empirical formula is C, essentially C1, F, again essentially F1, and then Cl2. So CFCl2. The molecular formula of X is the same as the empirical formula. Calculate the number of compound X molecules in 612 grams of a sample of compound X. Hence, calculate the number of atoms in 612 grams of compound X. So the first thing we need to do is work out, well, how many moles are there of compound X in this sample? To do that, we need to do the mass over the MR. So the MR of CFCl2 is 12 plus 19 plus 2 times 35.5, which is 102. And we can do that because, of course, the empirical formula, they tell us that X is the same as the molecular formula. So now that we know the MR of X, we can work out the moles by doing the mass, 612, and dividing it by that MR of 102. Now that gives us 6 moles of X. However, notice that the question isn't actually asking us about the number of moles of X. It's asking us about the number of molecules of X. And we should know that there's Avogadro's number of molecules in every mole. So here we need to do 6 of the moles times by Avogadro's number, 6.02 times 10 to the 23. That gives us 3.612 times 10 to the 24 molecules. Now, of course, if we look at the formula, we can see that each molecule of CFCl2 has 4 atoms within it. For this reason now, if we know how many molecules there are, all we need to do is multiply that through by 4 to find out the number of atoms. So here we need to do 4 times by 3.612 times 10 to the 24, and that gives us 1.4448 times 10 to the 25 atoms. And so that's the answer. So next we're asked to state and explain the trend in volatility of halogens from chlorine to iodine. Well, we should know that volatility is the tendency of a substance to vaporize in air. So if something is a gas at room temperature, then we can say it's highly volatile, whereas if it's a solid, then it has low volatility. So knowing the properties of the halogens, we know that at the top, fluorine and chlorine are gases, bromine's a liquid, and iodine is a solid. Therefore, we can say as we go down the group, the volatility decreases. Now here we need to know why this is the case. So we should know that as we go down the group, there's more and more shells, and therefore there's more electrons. Now because there's more electrons, we're going to have stronger and we're going to have more van der Waals interactions. Now, because we have those stronger intermolecular forces, we're going to require more energy to break them apart, and that is why the volatility decreases as we go down the group. Displacement reactions can be used to detect bromide ions in solution. A student bubbles some chlorine gas through a sample of bromide solution. Give the ionic equation for the above reaction. So just to remind you, in the periodic table, remember that as we go down the group, the reactivity decreases. Fluorine and then chlorine are the most reactive of the halogens. So for that reason here, when we bubble chlorine gas through a sample of bromide ions, because chlorine is more reactive than bromine, we're going to see this displacement reaction take place. So here we're going to have Cl2, which is a gas, plus Br minus, which is aqueous because it's an ion, and that's going to make Br2, which is a liquid, and Cl minus, which is aqueous. Now, because they're diatomic molecules, the Cl2 and the Br2, we need to balance this equation by adding 2's in front of the Br minus and the Cl minus. However, this is the general form of the ionic equation that we see with these halogen displacement reactions. And we're going to see these come up all the time. The most important thing is just to make sure that we know if that displacement reaction is possible. And so here this one is, because chlorine is more reactive than bromine, and therefore it can displace it. So now we're asked to state the main sulfur-containing product when Br minus and I minus ions react with concentrated sulfuric acid. And here, really, in a perfect world, we should just know these off by heart. We should know that when Br minus reacts with concentrated sulfuric acid, our main sulfur-containing product is SO2. However, I'm going to remind you of the equations that bring us to that point, because really we need these memorised, and I think this is one of the hardest parts of this course. So let's get started. So if we have H2SO4, our sulfuric acid, and we react it with NaBr, which could be the source of our Br minus ions, they react to give us HBr plus NaHSO4. So now this HBr that we've just made is going to react with some more sulfuric acid, and we end up making Br2 plus SO2 plus 2H2O. And so the main sulfur-containing product here is SO2. Of course, we could have just memorised that, but for extra revision, we're just checking this out as well. So next up, let's look at the reaction of iodide ions with sulfuric acid. So to start off, we have H2SO4, and let's say that we're reacting with sodium iodide as our source of iodide ions. Then we make Hi and NaHSO4. So out of these, the hydrogen iodide decomposes the easiest, and so the sulfuric acid is going to oxidize the hydrogen iodide to a couple of different extents, okay? So the first reaction we need to learn is that 2Hi reacts with those sulfuric acid to become iodine plus SO2 plus 2H2O. So the concentrated sulfuric acid oxidized the Hi, and the sulfuric acid itself got reduced to sulfur dioxide gas. Next up, the concentrated sulfuric acid is going to oxidize the Hi, and it will itself get reduced to sulfur. So here now, we have sulfur been formed. However, this is going to react again, okay? So the concentrated sulfuric acid is going to oxidize Hi, and it will itself be reduced to hydrogen sulfide. Now this here, this final oxidation, is going to give us our main sulfur-containing product of the reaction of concentrated sulfuric acid with iodide ions. So if you're not familiar with all those reactions, gosh, I recommend that you get learning them. So finally here, we're asked to explain why different sulfur-containing products are produced when Br minus and iodide ions react with concentrated sulfuric acid. So this question here is a really good one to help explain why on earth there's all of these different equations that we need to learn. And the reason why we get these different products is because as you go down the group of the halogens, the reducing power increases. So as a result of that, I minus is a better reducing agent than Br minus. And that is why we end up getting these different products when these different halide ions react with concentrated sulfuric acid. So we need to know that as we go down the group, the reducing power of those halide ions increases, and therefore I- is a better reducing agent than Br-. Fluorine forms a covalent bond called OF2. Here we're asked to draw a dot and cross diagram of OF2 showing the outer electrons only. So to answer this, we need to remember that each fluorine atom has 7 electrons in its outer shell, and oxygen has 6 electrons in its outer shell. Well, remember, to gain a full outer shell, fluorine and the oxygen both want 8 electrons in its outer shell. Now, the way that it can do this is if the oxygen and the fluorines each put 1 of their electrons into a shared region, the fluorine then gets that extra electron that it needed to have 8 electrons. And the oxygen, because it can do this twice, because there's 2 fluorines, can also gain those extra 2 electrons that it needed to get its full outer shell. And so therefore, this diagram that I've drawn out here is the one that we want to show for our dot and cross diagram of OF2. So next up, we're told that OF2 can react with SO2 as shown in the equation below. Here we're asked to state the oxidation state of fluorine in each species in the boxes provided. So I'm going to draw this out a bit bigger so we can see it more clearly. So here I've got OF2 plus SO2 goes to SO3 plus F2. So we should know that for fluorine, whenever fluorine is bonded to another substance, fluorine is special in the case that it always has an oxidation number of -1. So for that reason, we know that in this first molecule here, OF2, fluorine has an oxidation state of -1. Next up, we need to know what it is in F2. So because F2 is only bonded to itself, it means that the oxidation number of the fluorine has to be 0. And that's true of any molecule where we are just made up of one type of atom. So there we go. So it was -1 to begin with, and in F2 it is 0. And so that is our answer. So next up, we're asked to predict the bond angle in an OF2 molecule and explain your answer. So let's remind ourselves of the dot and cross diagram that we drew. We know that when we drew it out, we had the central oxygen atom. And around that central oxygen atom, we can see that we have 2 bonded pairs of electrons, and we have 2 lone pairs of electrons. And that's the important bit of information here that's going to help us work out this angle. So we're going to make that statement. We have 2 bonded pairs of electrons, and we have 2 lone pairs of electrons. Next up, we're going to make a really important statement that lone pairs repel more than bonded pairs. Now, because of this, we can state our bond angle. Now, the bond angle that I personally normally give is 104.5. However, any angle that you've learnt between 102 and 105 degrees is going to get you that mark. So don't worry if you don't give the exact same angle I've written down here, that's fine. Anything from 102 to 105. So now we're asked to predict the shape of the molecules SO2 and SO3. So if we do a dot and cross diagram for this, we'll be able to work it out. So I know that both sulfur and oxygen have 6 electrons in their outer shell because they're both in group 6. Now for that reason, it's going to be a slightly different example, this one. Because what we're going to do is the oxygen is going to get its full outer shell by borrowing 2 electrons from the sulfur. So there's going to be a double bond between each sulfur and each oxygen. That sorts out the oxygens with their full outer shell. However, we also have an additional lone pair of electrons on the sulfur. So due to this and the fact that we know that lone pairs repel more than bonded pairs, what we're going to see with SO2 is a non-linear or a bent shape. Because you only have 2 bonds, however, that's not going to be in a linear structure due to the presence of that lone pair. So now if we think about SO3, so again, each oxygen needs to gain 2 electrons. Here what we can do is the sulfur can give 2 of its electrons to do that. So what we have here when we do this dot and cross is we can see that we have 3 regions of bonded pairs of electrons in the SO3. And all of these bonded pairs are going to repel equally. So the result of this is we're going to get a trigonal planar shape. And so that is the shape of SO3. Sulfur hexafluoride, SF6, exists as a non-polar covalent molecule. Predict the shape of the molecule and explain your answer. Okay, so here we know that sulfur has 6 electrons in its outer shell, and fluorine has 7, so the fluorine needs to gain 1 electron. So it can gain 1 from each of those electrons in the sulfur, which means that we get 6 bonded pairs of electrons surrounding the sulfur. Now, whenever we have 6 bonded pairs of electrons, that tells us that we have an octahedral shape. And in terms of our explanation, the reason for this is that the sulfur has those 6 bonded pairs of electrons and no lone pairs, and electron pairs will repel each other to achieve maximum stability. So there we have it. That is the shape of the molecule, octahedral, and the explanation as to why this particular molecule, SF6, forms this octahedral shape. Crude oil is the source that is used to produce naphtha. Naphtha is the mixture of hydrocarbon molecules. The diagram below shows the process that can be used to produce a sample of naphtha. State what's meant by the term hydrocarbon. Now, this is a really important definition. There's no way you can go into your exam without knowing this. So a hydrocarbon is a molecule that contains carbon and hydrogen, and here's the important bit, only. Okay, you can't just say it's a molecule containing carbon and hydrogen. You're not going to get the mark at all there. You have to say only. And so there you are, that's the definition. It's nice and simple, really. So hopefully you can get memorising that now. So cracking converts the alkane dodecane into a more useful alkane and alkenes. Give the balanced chemical equation for the complete combustion of dodecane. So they've given us the formula helpfully here. It's C12H26. We're going to add oxygen because we're combusting it. And because it says complete combustion, we know it's only going to make carbon dioxide and water. So now we need to balance it. Start by looking at the number of carbons in dodecane. There's 12. Now that means that we're going to need to make 12 carbon dioxides. Now in the dodecane we have 26 hydrogens. That tells us that we need 13 waters. So now we need to have a think about how many oxygens we're going to need. So you can see here that we have 24 oxygens, so 12 times 2, in the CO2s. And we've got 13 oxygens in the waters. So tallying those together, we end up getting 37 oxygens in total. Now because we've got O2 as a reactant, we need to halve the 37 to see how many O2s we're going to need. And 37 divided by 2 gives us 18.5. And so that's what we need to fill in here. Okay, so I'm going to put next to that oxygen 18.5. And then we've got our perfectly balanced equation here now. There you go. Now we're asked to identify a reagent that could be used to show that the cracking product contains a CC double bond. And we're asked to include relevant observations. So this is a very important test that we need to know. So the test for the CC double bond is the bromine water test. So we need to know whenever we need to test for the presence of alkenes, we just add bromine water. And the observation is going to be what tells us if we have alkenes present or not. Bromine water will be orange in colour, and if there's a CC double bond present, it will become colourless. Okay, so next up, ethene reacts with Br2 to form 1,2-dibromoethane. Now we need to name the type of reaction. Well, ethene has that CC double bond, and it will crack open to react with that Br2. So this is called an addition reaction because you have 2 reactants and you make just 1 product. Now we're asked to outline the mechanism for this conversion. So this is an electrophilic addition mechanism. I'm going to start off by drawing my ethene, and I know that it's about to react with bromine as the question states. So I'm going to put bromine next to the ethene, I know that that double bond polarises the bromine, and it repels away the electrons in that covalent bond towards the far bromine. That induces a dipole on the bromine, and then we need to think about curly arrows. So we're going to have one curly arrow going from the bond between the bromines towards the delta negative bromine, and we have another curly arrow going from the double bond to the delta positive bromine. Now what's happened here is we've broken that double bond, but we've formed a new bond between one of those carbon atoms and the bromine. However, we've also broken the bond between the two bromines. That leaves us with a carbocation and a bromine ion with a lone pair. Now the electrons in that lone pair are going to move towards that carbocation, and that leaves us with our final product. That leaves us with 1,2-dibromomethane. And there you have it, that is our mechanism. And this is your standard electrophilic addition mechanism. You can apply it to lots of different molecules though. However, the key thing to look out for though is it having that CC double bond. If it has that CC double bond, then you can apply this exact method to it, even if actually the molecule's a bit more complicated. This will still apply. Addition polymers are made by the polymerization of alkenes. Here we're asked to consider the following polymer, and we need to draw the monomer that is used to form this polymer. So this is a bit of a tricky one, I think. What I'd recommend that we do here is we try and find the repeat unit. So I'm going to show you this here. So starting from the left-hand side, I can see that if I trace over this region here, I can make up the shape of just a repeat of that particular shape, of that particular part of the molecule. So if I zoom in and have a look, say at the blue one in the middle of these, I know that addition polymers have to form around a central CC double bond. And around that, I'm going to essentially break open that double bond and form the open arms of that polymer. So if we try and visualise this as the alkene it would have been, we can see that there would have been some H's on it, and these would have been the bits where the arms open up when that double bond breaks to connect it onto the other monomers. So here, where I try and translate this, you should be able to see that this region is the same part on the monomer as on the polymer. And here as well, you can see that this region here is equivalent to this region here on the polymer molecule. So there we have it, okay? That is the monomer that would be used to form the above polymer. Now, if you prefer, we could draw this in skeletal formula as well. That's absolutely fine. I can see here that there's 5 carbons in my longest carbon chain. So I can do a zigzag that has 5 points on it, and it has a double bond on the second carbon there. So there we go, either of those are going to get you the mark. Next up, we're asked to state the IUPAC name of the identified monomer. So looking at this, first thing we need to do is work out what the longest carbon chain is. And as I mentioned, it has 5 carbons in the longest carbon chain. I know that it has a double bond, and using the lowest number possible, it is on the second carbon, that double bond. So that means that we have pent because we have 5 carbons, 2 because the double bond is on the second carbon, and ene because we have this CC double bond. The graph shows a sketch of the first ionisation energy of the elements from neon to aluminium. Describe what's meant by the first ionisation energy. And this is a really, really common definition that we need to know inside out, okay? So let me tell it to you. The first ionisation energy is the energy required to remove 1 electron from each atom in 1 mole of gaseous atoms. So it's quite a lengthy definition, but there's a few really, really important points within that. Obviously, we need to know that it's the energy required for something to happen, but we need to know that we're referring to 1 mole of atoms. We're not just talking about atoms, it's 1 mole of atoms. If we miss that word, then we lose out on a mark. We also need to make it clear that this is in the gaseous state. These numbers only apply to the gaseous state, so make sure you include that too. So now we're asked to construct an equation to illustrate the process which occurs showing the first ionisation energy of neon. And here we need to include state symbols, and we always should include state symbols when we're doing ionisation energy equations. So here we have neon in the gaseous form, as I said was so important in that definition, goes to Ne plus gaseous ions plus an electron. So notice there's just 1 mole of each of those, as the definition stated as well, and everything is gaseous. So you can see that they sort of tie in together really well there and help really solidify your understanding, I hope. The neon atom and the magnesium 2+ ion have the same number of electrons, but the first ionisation energy of neon is lower than the third ionisation energy of magnesium. Here we're asked to state 2 reasons for the above trend. So the first ionisation energy of neon involves removing an electron from a neon atom. And the third ionisation energy of Mg2+ involves removing an electron from the Mg2+ ion. So if we compare the neon atom and the Mg2+ ion, we will see that they're actually in the same shell and they have the same number of electrons. So although of course magnesium, the atom, has 1 additional shell, by the time it's lost 2 electrons, it has the exact same electronic configuration as neon. So it is technically in the same shell. So the main difference though, yes, they're in that same shell. However, the magnesium 2+ is going to have more protons because it has the number of protons that magnesium has. So if it has more protons, it's going to have a more positive nuclear charge. And that's going to have a direct impact on that ionisation energy, because if it's got a more positive nuclear charge, it's going to require more energy to remove the electron. Another consequence as well, though, is as it's more positive, it's also going to have a smaller radius, because it's going to be attracting that outer shell closer towards the nucleus. So 2 things we can say here. The first thing that we can state, a reason for this trend, is that the Mg2+ ion is smaller than the neon atom. And the second thing we can say is that the Mg2+ ion has more protons than the neon atom. So both of these are reasons why third ionisation energy of Mg2+ is going to be bigger than that first ionisation energy of neon, and why we need more energy to remove that electron from Mg2+ than neon. So now we're asked to sketch the graph to show the trend in the radius of elements from sodium to chlorine. So we should know that all of these are in the same period, and therefore they are all in the same shell, and they have the same shielding. However, as you go across the period, the number of protons increases, as does the number of electrons. Now the consequence of this is that shell is going to get attracted towards the nucleus more as the proton number increases. And therefore, as you go across this period, the atomic radius is going to decrease. You don't necessarily have to draw a straight line like I have here. However, the general trend should be clearly a downward trend. That is what's going to get you your first mark here. That's going to be the mark for the graph. However, we need to explain our answer too. So the key things that we need to state here, and I've essentially mentioned a lot of these here as well. We need to state that the electrons are added to the same shell, or we could say that the shielding remains the same. However, there are more protons as you go across the period. And finally, we can conclude by saying that there is therefore a greater attraction. And that is what has the knock-on effect of decreasing the radius. And there we have it. There are our 3 marks that we need to state to get our full marks in this question. Here we're asked to consider the following equation. We're told that the above reaction was followed by measuring the concentration of A present in the mixture at regular time intervals. And here we've got a little graph with the concentration of A and time. Here we're asked to calculate the average rate of reaction during 8,000 seconds. Now the important word here is average. They're not asking us to find it at that point. where we would then do a tangent and work out the gradient. No, because it's the average rate of reaction, we just need to calculate the change in the concentration of A and divide it by the time that took. So if we look at this graph, we can see that at time t equals 0, we have a concentration of 0.018. However, if we have a look at when time t equals 8,000 seconds, I can see that we seem to have a concentration of 0.006 moles per decimeter cubed. And so therefore we can get the average rate is equal to that change in concentration, 0.018 minus 0.006, and we divide it by the time that took, which is 8,000 seconds. So popping that into the calculator, I end up getting 1.5 times 10 to the minus 6. And for that unit, because the concentration is in moles per decimeter cubed, and we're dividing by time in seconds, we have 1.5 times 10 to the minus 6 moles per decimeter cubed, and then per second, because it's over time, so divided by those seconds. When the frequency of successful collisions between reactant particles is increased, the rate of reaction also increases. Here we need to explain why an increase in temperature produces this effect. And this is a very common question that we should know quite well. So we should understand that at higher temperatures, the average kinetic energy of our particles will increase. Therefore, we're going to have a greater proportion of particles whose energy exceeds that activation energy. So that is why the rate of reaction will increase when we have a higher temperature. So I hope that makes sense. If you weren't familiar with those two really key points, then make sure that you go away and get learning them. So now we're given a diagram which shows the Maxwell-Boltzmann distribution of molecular energies in a gas at two different temperatures. Here we need to complete the diagram by labelling the axis. So to answer this, all we need to do is to remember what those axes are on a Maxwell-Boltzmann distribution graph. We need to know that the energy is found on the x-axis, and the y-axis is the number of molecules. However, you might have learnt that as the proportion, or the percentage, or the fraction of molecules. All of those would still give you the right mark there. So now we need to state the effect of a solid catalyst on the shape of either of these distributions. And this is almost a bit of a trick question, because the answer is that there's no effect. Let me remind you of what actually happens on these graphs when we do have a catalyst. Obviously we've got the general shape of the curve, and we should know that the activation energy is a line around about here, a nice vertical line. And what will happen when we add a catalyst is we lower that activation energy. So yes, that line will change its position, however the shape doesn't change. So now we're asked to explain how a catalyst speeds up a chemical reaction. So we need to know that a catalyst will provide an alternative route or an alternative reaction pathway which has a lower activation energy. And those are our 2 points that we need to get across to get our 2 marks here. Firstly, we need to express the fact that we've got this alternative route. And secondly, we need to make it clear that that route has a lower activation energy. And there you have it. So if any of this you didn't know, just get some flashcards made on all of these notes that we've written and then get learning them, and then you're sure to get them right when they come up in your exam. Hess's law is used to calculate the enthalpy change of a reaction for when it's difficult to determine the value experimentally. Here we're asked to state Hess's law. So we should know that Hess's law tells us that the enthalpy change in a reaction is independent of the route. So it only depends on the initial and the final states. So a perfect little definition to give here is simply that the enthalpy change in a reaction is independent of the route taken. Gaseous buta-1,3-diene burns as shown by the equation below. Use the average bond enthalpy data given below to answer the following questions. So first up, they simply want us to describe what's meant by the term average bond enthalpy. So we should know that the average bond enthalpy is the average enthalpy change when 1 mole of gaseous covalent bonds are broken. And so see, that's just a simple little definition. And so far on this page, we've had 2 definitions. If you're not familiar with these definitions, then I recommend that you pause the video right about now and you get writing them down so that you can go away and get learning them. There is absolutely no time like the present, okay? So make sure you get working on that now. So now we're asked to calculate the enthalpy change which occurs when all the bonds in the reactants shown in the equation are broken. So we need to look at the bonds broken here, okay? So I've included our equation just here so that we can look at it. Now the thing that I like to do in these questions is just draw out the structures, because to be perfectly honest, it's very easy to miss something if we're just visualising it in our head. So by drawing it properly, that should minimise it. The same goes if they give you something like skeletal formula. Make sure you draw it out properly, showing every single bond, because otherwise, gosh, I bet you'll miss something. Okay, so we've got the structure of the 1,3-butadiene, and we've got the structure of the oxygen. So now, if we look through this one at a time, I can see that I've got 2 of the CC double bonds. So I'm going to do 2 times 611. And then I am going to add on to this now how many CC bonds there are. And here I can see that there's just 1 CC bond. So I'm going to do plus 348. Next up, let's look at the carbon to hydrogen bonds. So here I have 1, 2, 3, 4, 5, 6 of those. So I'm going to add on 6 times 413, because that is the average bond enthalpy of a CH bond. So that's everything there from the alkene. But now let's not forget that we also have 5.5 oxygens. So that's O to O bonds. So I'm going to add on here finally 5.5 times by 493. So that there, if we tap that all into the calculator, gives me a total enthalpy change of 6,787 kilojoules per mole. So there we go, we have got our first mark. Next up, we're asked to calculate the enthalpy change which occurs when all the bonds in the products shown in the equation are formed. So again, I'm not going to assume that I'm going to get this perfect. I'm going to draw this out just to make sure that I'm not skipping over anything. So I've got my C to O double bond, and I can see in every single carbon dioxide I have 2 of those, and I have 4 CO2s. Same goes for the water. I have 2 OHs, and I have 3 H2Os in total. So for that reason, if we're looking at that C double bond O group, I can see I'm going to have 8 of those in total, because I have 4 times 2. So I'm going to do 8 times by 743. And finally here, I can see that I've got 2 OHs for every 1 water, and I've got 3 waters. So 3 times 2 gives me 6 times 464. Now again, time just to put this into the calculator here. When I do this, I end up finding that that enthalpy change is equal to 8,728 kilojoules per mole. So finally for this part, it says hence calculate the enthalpy change for the complete combustion of but-1,3-diene as shown in the diagram below. So looking at this here, I know that it doesn't matter that it's enthalpy change for combustion or anything, we don't want to be misled by that statement. It's just the enthalpy change of the reaction that they've given, because it happens to be a combustion reaction. And using bond enthalpies, we can work this out by saying that the enthalpy change is equal to the bonds broken minus the bonds made. So that gives us here then 6,787 minus 8,728. And that gives us minus 1,941 kilojoules per mole. And that is the enthalpy change for the complete combustion of but-1,3-diene. The equation below shows the formation of but-1,3-diene. So we can see it's 4C plus 3H2 makes but-1,3-diene. Here we're asked to use the following data and your answer from part 6BIV to calculate the standard enthalpy change of formation of buta-1,3-diene. So we just worked out the enthalpy change of combustion of buta-1,3-diene, didn't we? And we said that was equal to minus 1,941. So because that's a combustion, that's important. Here we're being asked to calculate the standard enthalpy change of formation of buta-1,3-diene. And that's the equation that they gave us at the top of this page here. So what I'm going to do is I'm going to write that reaction whose enthalpy change I want to find along the top of this. So I've got 4C plus 3H2 goes to C4H6, and I'm calling that delta H because that's what I need to find. Well, if along the bottom here, I write the products of combustion of buta-1,3-diene. So going back from the previous page, we know that the but-1,3-diene combusted with oxygen to make 4CO2 plus 3H2O. So I can do an arrow node going down from that alkene to those combustion products. And I can label that with the enthalpy change of combustion, the minus 1,941. Now if I think of the other information that I was given, I've essentially been given the combustion of carbon to make CO2. Or we could think of it as the formation of CO2. So if I do 4 times minus 394, that would make the 4 CO2s that I have here. And likewise, I can do the same with the water. I can say, well, H2 with oxygen makes H2O. Well, here I've got 3 H2Os to make. So if I do 3 times minus 286, I will get that enthalpy change too. Now looking at this left-hand side, obviously here we've got 4 times minus 394 plus 3 times minus 286. What I like to do at this point, as you can see, is I just like to tally up what that is there and then. I want to simplify that as much as I can now so that I'm not worrying about that later down the line. So when I put this into the calculator, I get minus 2,434. So now let's think about Hess's law. Remember, we said that Hess's law tells us that the enthalpy change is the same regardless of the route that we take. So yes, we're starting here at the 4C plus 3H2. We're also ending at the C4H6. We need that enthalpy change going from left to right, but we can take a different route. We can go down and then up. So the enthalpy change can be equal to going down, that's minus 2,434, and then we need to go up. Now notice that going up, we're going in the opposite direction to that pink arrow. That means we're going in the opposite direction to that enthalpy change of minus 1,941. Now, there's a really easy remedy to this. All we need to do if we're going in the opposite direction to an enthalpy change is we reverse its sign. So here it was negative, and so I'm going to change it to positive. So as you can see here at the minute, I'm saying that my delta H is equal to minus 2,434 as I go down, and then as I go up, I'm going in the opposite direction to that pink arrow, so I'm going to change it to plus 1,941. Now, if I pop that into the calculator then, I have my enthalpy change. I have delta H equals minus 493 kilojoules per mole, and that there is our answer.
Ouch! This is why in some videos I explain scratches.